let's figure out how we can create this stylized galaxy using simulation nodes and a few basic math operations. It might be a bit longer than usual, and that's why we're going to keep chapters so that you can skip to the exact regions that you want, and for any math involved, we're going to explain each step and why we're doing it. So that way, you'll be able to use the techniques learned in this video to create your own animations as well. So with that, let's actually start step by step on how we can create this black hole ourselves. So in our default scene, we'll bring our cursor to the junction of these two windows, click and drag to create a new window, and we'll change it from the 3D viewport to the geometry node editor. Then we'll press this plus button to create a new geometry node tree, select the group input and tap X to delete it. Now we essentially want a plane on which we're going to distribute a bunch of points, and we've done that in multiple videos before, so you should be able to guess that we're going to use a grid node and plug this mesh into the group output. Now we want this to be a really large plane, so we'll increase the size on the X and the Y to something like 10 so that we get 5 meters on either sides. Now we want to distribute points on the faces, so we search for a distribute points on faces node and plug that in after the grid. Next, we can increase the density to something high like 10,000, and this gives us a lot of points to work with. Now we don't want the points to start off in this square shape, we want it to start off in a circular shape, so we can search for a delete geometry node and delete all the points that are present further than 5 units from the center. So we know that the position of every single point is stored in the position node, and we can find out the length of this position by searching for a vector math node and changing this from add to length. Then by plugging the position in here, we get the length of the vector or its position vector. So just to explain it, if we have a point present here, the position is going to give us a vector that goes from the origin to the point like this. And by finding the length, we don't care about the direction anymore, so it could be in any direction, but what we get is this length of the vector. So now we have to compare if that length is greater or lesser than 5. So to compare anything, we have a compare node, so we press Shift A, search for a compare, and we can plug this value into the first socket, and we want to delete it if this position length is greater than 5. So we change this B to 5 and plug this result into the selection, and there we get a circle with radius 5 units. The next part is actually getting these particles to rotate. So let's go through the math as to how we're going to be getting them to rotate. From the previous section, we already saw that if we have this as the origin and we have this as some point, when we use this position node, we get this particular vector. Now, if we multiply this vector by -1, we actually reverse the direction of the vector, and instead we get a vector that goes from P towards O, and it goes like that. Now what we can do is we can rotate this vector by 90 degrees to move it to this new direction, and then if we move this point in this direction on one frame by scaling this down and maybe moving this to a new point over here, on the next frame the evaluation will have a vector like this, and then we rotate it and it comes like this, and we move it so that it moves here. So if you actually take a look at the trajectory of this point, it's going to slowly spiral outward, but in an almost circular manner. So this sort of a spiral is what we want. However, we don't want it to spiral outward, we want it to spiral inward. So to get it to spiral inward, what we do is instead of rotating this vector by 90 degrees, we rotate it by some value lesser than 90 degrees and continue the same process by scaling this vector down and putting the new position there. So this way, if you actually look at it, now it's actually closer to the origin, and this time it's going to follow a spiral path that slowly goes into the origin, which is exactly what we want. So let's take a look at us creating that step by step. Since we want these to move every single frame and evaluate every single frame, we're going to use simulation nodes to do that. So we move the group output to the side and search for a simulation zone. Now we take this delete geometry, plug that into the simulation input, and take the output from the simulation output and plug that into the group output. Then since we want to move the position of the points, we have to use a set position node, so we search for a set position and plug that in after the simulation input. Now for the offset, we already said that we want the position of each point, then we want to inverse the position, and then we want to rotate it. So let's search for a position node and then search for a vector math node, change to scale. So change this from add to scale and just scale it by -1, and this reverses the direction of the position vector. Next, we need to rotate this vector by 90 degrees. So to rotate it, we search for a vector rotate node, and we want to rotate this vector about its origin itself, which is about the point, and we want to rotate it about the z-axis so that it rotates along the plane on which these points are present. So that's why the axis is going to be 0 on the x, 0 on the y, and 1 on the z-axis. Next, we wanted to rotate it by something by less than 90 degrees, but first let's see what happens if we rotate by 90 degrees. Now if we were to plug this directly into the offset, remember each vector is fairly large, so it's going to move by a huge amount every single frame. So when we play the animation, it just spreads out really fast, so that's not too helpful. We can bring that down by taking the scale node, pressing Shift D, plugging that over here and scaling it down by a small number, so let's say 0.1, and then running the simulation again again by going to frame 0 and running it. So now you can see how these parts are actually rotating, but as they rotate, they're also slowly growing. So to prevent it from slowly growing, all we do is change this angle from 90 to something smaller, let's say 75 degrees, and then run the simulation again. So this time it's shrinking and spiraling in towards the center. Now that's great, but there are a few problems with this. The first thing is every particle in this simulation is spinning at the same rate. However, around a galaxy, particles or planets or whatever that's present near the center would actually be moving much faster than particles present towards the edge. And so we're going to have to control that motion as well. We'll deal with that in a second after we actually figure out how to get more points to be present, because right now if all the particles reach the center, we then after a few frames have just nothing but a clump of points present in the absolute center. So one thing that you could do is add in new points every single frame and delete the points that reach the center, but that takes a little bit more working, and since we're not using the actual velocity of the individual points, I think it's smarter to take the points that reach some region within the center and just respawning them to the outermost edge, and that will require math that will actually help you in many other animations as well. So let's get into that. What we want is these particles to get a new position if they reach within a certain distance from the center. So for that, since we want to set their position, we take a set position node. We can take this and just press Shift D and plug that in over here. Now we want this set position node to work only on particles that are present within some distance from the center. So let's take 1 meter from the center. So for that, we have to actually search for a position node and do the exact same thing that we did for deleting the particles over here. We want to find the length and we want to see that if it is smaller than or lesser than a certain value, then only then should it work. So we can actually just press Shift D after selecting those 3 nodes and plugging them in over here and removing this position node over here. Now we want it to be lesser than 1, so we change this from greater than to less than, and we change this B value to 1. So if the position of a particle has a length lesser than 1, only then should this set position work. So we take this result and plug that into the selection. Now for the actual value of the set position, we're not going to use the offset because we just want to set the position directly. So we have to set the position onto the circumference of this circle with radius 5 units. So how do we select a random point on the circle? For a random point, since it's a circle, we can use the polar coordinates, and we know that the polar coordinates use sine and cosine of some angle. So let's press Shift A and search for a math node and change this from add to sine, which is present under the trigonometric functions. Now we can take a random value node and change this to angles by changing the min to 0 and having a max as 2 pi, which is 1 full circle in radians. Now 2 pi, you can write 2 star pi, or you can directly type in TAU, which is tau, which is also equal to 2 pi. Now if we plug this value in, the output of this is going to be the sine of some angle going from 0 to 2 pi. Remember, sine gives an output from -1 to 1. So the output of this is also going to be a random value between -1 and 1. Now if we take the cosine of this particular value itself, we will get a random number that lies on the circumference of the unit circle if we were to consider this sine as the x value and the cosine as the y value. So let's Shift D on both the random value node and the sine node to create duplicates and change the sine from sine to cosine. Now we want to use the sine on the x-axis and the cosine on the y-axis, so we search for a combine xyz and plug this into the x and this into the y. Now if we actually plug this value into the position, since we're using the same seed value on both of these, we should get a random value on the unit circle. But we don't want it to go on the unit circle, we want it to get shifted to a circle with radius of 5. So for that we search for another math node and we simply multiply this by 5. Now you see it goes into a single line because this is a vector output and we're using a normal math node, so we have to search for a vector math node and then change this to scale and scale it up by 5 units. Now let's plug this into the position, and now when we play the animation, you should see that every time a point reaches the center or within 1 unit, it gets shifted back out to the edge, and that gives it this particular animation. Now to increase the randomness that's occurring, what we can do is take a scene time node and plug this frame into the ID for both the random values. So then if you actually play this, you see we get all of these points going into specific regions. It looks like the number of points are decreasing. The reason that's happening is because multiple points that reach this central region is being assigned the same position. So to change this, what we do is we search for an index node because this is unique for every single point, and we just add that to the frame number. So we search for a math node and we add this frame number to the index, or the index to the frame number, and plug that into the ID of both the random values. values. So now when you play it, you get a truly random distribution of points just like this. Now what we want is the regions towards the center should be speeding up as compared to the regions towards the edges. To do that, we have to play around with this set position itself so that we can control the velocities. Now we want the velocities to speed up according to their position. So we use another scale node. So we can take this scale node, press Shift D and plug that in over here and scale it based on the length of the position. So we take this position node and we search for a vector math length. So we can take this length over here and press Shift D to plug it in over here. And if we directly plug this in, the further away the point is, the faster it will move. We don't want that. We want it such that the further away it is, the slower the particle becomes. To do that, we can actually search for a math node and change it to divide. So that's because, remember, if we take 1 divided by some number, we will get a larger output if the number is smaller, and we'll get a smaller output if the number is larger. So if we plug this into the second socket and we change the first socket to 1, we get 1 divided by the length, and if that length is greater, the output is going to be smaller. If that length is smaller, the output is going to be relatively larger. So let's take this and plug that into the scale. However, right now this value is going to be fairly small, and in case we want to scale it up, we can search for another math node and change this to multiply and just multiply it by some number that we feel happy with. So let's start off with 2 and see what we need from there. So right now we can see that the particles near the center are moving faster than the particles outside, but it's not too noticeable. So let's start increasing the value to maybe 5 and then play the animation again. Now with a value of 5, it's too fast for me to actually tell the difference. So what I'll do is I'll change this scale value down to something like 0.01 so that overall every particle becomes much slower and we'll actually be able to see the motion of these particles. So now when we play the animation by going back to frame 0 and refreshing it, you can see each of these particles are moving, but as they move closer towards the center, they start moving even faster. So we can exaggerate that effect by increasing this value to an even larger number, let's say maybe 7, and then restarting the animation, and this looks fine. However, this still does not look like an actual galaxy, and that's because galaxies have these nice arms that are present around them, and this is just a random distribution about the entire plane. So to create areas with higher densities and regions with lower densities, what we can do is actually change the seed on either the sine or the cosine values. If the seeds are not the same, what will happen is we'll have constructive interference in certain areas and destructive interference in other areas. So some areas will keep getting more number of particles and some areas will keep getting lesser number of particles due to the nature of sine and cos. So let's just change the seed to something random, and now when we play the animation, everything does get a little slower, but after a while you should be able to see some sort of clumping happening. So in my region, or in my case, you can see that there are spirals being formed just like this that go all the way around. Hopefully the spirals are visible. Now there's a few things to this. The first thing is that I want to increase the end frame to a really large number so that it doesn't keep resetting. So let's change it to 800 so that we can actually see these spirals being created. And the next thing is we see these very clear-cut edges that are present on these 4 regions. So to fix that, what we'll actually do is while instancing points, we'll not instance points that have too far of a distance from their neighbors. So that way most of these points will get removed, and by removing those points, it'll not be this noticeable of an edge. But that's essentially all there is during the simulation section of this video. Now we're gonna have to actually go on to this section after the simulation. So if you're happy with this, go ahead and go to the physics properties, click simulation nodes and press this bake button. Remember that if you actually take a look at it, we don't get that spiral nature until this first set of points goes all the way to the center and gets shifted back out to the edges. So you have to take a look at what frame that's happening on. So in my case, that is actually happening all the way at frame 236 approximately. So maybe when I actually render the animation, I'm going to start it after 236. So if I want it to be 10 seconds long, what I'm going to do is make 236 plus 10 seconds, which is 300 frames. So I have to end it at 536, and then I'm going to click this bake button. So let's press this bake button so that the simulation does not have to rebake every single time, and we can actually change this start frame to that frame 236. So let's press bake and see what happens. Remember, to actually bake this simulation, you have to save the Blender file first. So just make sure that it is saved. Now once it's baked, you can change the start frame to 236, and then when you play the animation, it's gonna nicely animate and you won't be able to make changes to that particular section. However, now what we're going to do is we're going to press Shift A and search for an instance on points node so that we can actually instance some object objects onto these points. Now for the instance, I'm going to use an icosphere, but I'm going to reduce the radius down to something like 0.02 and then plug that into the instance. So now we have one icosphere on every single one of the points that are present. However, since I want a few of these to not have icospheres, I'm going to use the selection bar. So now how do we select these points? The first thing is, for every point we can search for the nearest neighbor. For that we search for an index of nearest node, and by plugging in the position of every point we will get the index of the particle that is nearest to it. So we search for a position node and plug the position into the position. Now because my PC is lagging due to also recording at the same time, I'm going to go ahead and just mute this instance on point so that it's a bit faster on my laptop. Next, we have the index of the nearest, but we want to actually find the position of the particle that's there at this index. So for that we search for an evaluate at index node and we plug this index in here, and for the value we want it to be the position, which is a vector value, so we change this float to vector and we plug the position in here. So now we have the position of the particle and the position of the particle that's nearest to it. To find the distance between them, we search for a vector math node and we change the type from add to distance. Then we can simply plug this value in here and the position into this socket, and we can compare this distance to a number using a compare node. So we search for the compare node, plug this in here, and we want to use this instance on points only if their distance is less than a specific value. So let's say less than maybe 0.2, and that is going to go into the selection. So now let's just unmute this to see the effect, and not too many points have been deleted. So let's delete a few more points by changing this from 0.2 to maybe 0.02. And now you see a lot of the points have been deleted and the spirals just look a lot better. So you can experiment with this value to get the exact distribution that you want, but I think this looks good enough. So now that we have these galaxy spirals, I also don't want particles that are present too far away to be in the render. I want those to also be removed. So what we can do is we can say that if these particles are too far away, then we don't instance these icospheres onto them as well. For that, we have to use this selection itself, and we just want to use Boolean math so that we can check for both of them. So we search for a Boolean math node, plug that in, and since we want both the conditions to be there, we keep it on and itself. Now the second thing is if the position is greater than a specific value. So that is the same as what we've used over here, which is position length less than. So let's take these three, press Shift D, and then plug this into this second socket of the Boolean math node. So now this length is evidently too small, so let's increase that to maybe 6, and that just deletes a few of those stray points that were present over here and makes it look a little better. So that way we actually get the spiraling galaxy. The last few things that we have to do is go ahead and just set material. So let's press Shift A, search for a set material. You can always set smooth if you want as well by searching for a set shade smooth node. However, I won't do that as of now, and just choose the default material over here. Then go to the shader editor and play around with the material. If you can't find it, press this period on your numpad to centralize all of the nodes. And essentially what we want is we want them to be emissive and we want them to have some gradient so that the particles nearby the center are the brightest and particles far off are the least bright. But before we actually start the shading and all of that, we'll set all of our defaults. So let's go to our render properties, switch on bloom and screen space reflections. Under screen space reflections, let's also switch on refraction because we're going to need it for the central black hole. Then we'll go to our output properties, change the frame rate to 30 frames per second and change the output folder to wherever you want it to be, along with changing the file format to your suited formats. I'm going to change it to FFmpeg video with a container of MPEG-4 and the output quality of perceptually lossless. Now we want this gradient to be present from the center outward, and since we're using instances, we get individual gradients from each point if we were to use texture coordinates set to object. However, we can simply alleviate that by first adding in the black hole and using that as the object. So let's go ahead and search for a mesh sphere and then press Ctrl 2 to add in a subdivision surface of level 2 and go to object, set shade smooth. Now we can select our geometry node object again and then search for a gradient node or a gradient texture node and Ctrl Shift click with the node wrangler switched on to actually preview what the gradient looks like. And of course, to actually see these changes, you have to change your viewport shading from solid to rendered. Now if we switch off overlays, this is what it currently looks like, and clearly no gradient can be seen. So to fix that, again with the node wrangler switched on, press Ctrl T to add in a texture coordinate and mapping nodes, and this time change from generated to object. If you switch to object, you see the gradient happens for each of the particles separately. You can test that out by just playing around with the scale, and if you increase the scale, you can see how each particle is getting a gradient from the left to right. However, that's not what we want. We want it to be about the entire object. So for the object, we'll just select the sphere that we created, and that way you get it about the object. Now let's reduce the scale back to 1 and change this from linear to spherical. After that, if you don't see it, you can start reducing the scale on all of the axes and you should be able to see the nice gradient. Next, we want this gradient to go through a color ramp. So we search for a color ramp, plug that in after the color, and now we choose the colors according to what we want. This side is the outer edges, so maybe we can give that a nice bluish color, and then the absolute inner edge will keep as white, but in between we'll add in another marker by pressing this plus button and then making this maybe a slightly brighter blue as well, and maybe these could be our colors. Next, we can position these around better and change this from linear to ease. Once you're done with that, remember this is the color for the emission, so we can plug that in over here and we can just increase the emission strength to something like 5 or 10 to get some nice blue. To actually see that, we have to select the principal BSD and Control Shift click it so that it becomes the material that goes into the surface of the material output, and that way we have the bloom for our particles. To see this better, you can go to the world properties and change the background all the way to black. Next, we have to deal with the material of our UV sphere, and we're going to use a material very similar to this particular tutorial that was released fairly long ago, but be sure to check out that tutorial because it might come out handy to you as well. For this, we're going to press new and we're going to select the principal BSDF and press X to delete it. Then we're going to search for a refraction BSDF and plug that into the surface. Next, to actually see the effects of this refraction, we have to go to the material properties over here, go to the settings and change the blend mode from opaque to alpha blend, switch off show backface and switch on screen space refractions. With that, we should be able to see some sort of refraction as you can see happening over here. However, this isn't the exact type of refraction we want. We want the IOR to change according to the distance from the center. For that, we have our layer weight node and we can take facing and plug that into the IOR. Now, if we start increasing the blend mode, we should be able to see more refraction. So let's increase that to something like 0.9 and now we see refractions, but it's not exactly what we want because it's going towards the center. We want it to go around the sphere. So to get it to go around the sphere, all we have to do is search for a math node and switch this from add to power and change the power to -1, and that way it should go nicely around the object. So if you were to render it from a side angle like this, you'd actually get the black hole looking like a realistic black hole. However, I think for this animation, I'm just going to render it from the top so the refraction doesn't have too much of a role to play, but it's still useful to know. The last thing that you have to do for your scene setup is set the camera. So let's just select the camera, press Alt G to clear location, Alt R to clear rotation, and then press GZ and bring it up by quite a bit. So maybe let's say 10 units up, and then press 0 to go into your camera view. Then you can press GZ and continue moving it up till your entire galaxy fits within the camera. And of course, you can play around with the focal length and things like that. Also the contrast, the look and everything. But once you're happy with the way everything looks, go ahead and press render animation. Hopefully you learned something useful from this tutorial, and simulation nodes is starting to get less daunting. The power of simulation nodes is really high. So it's definitely something that's worth adding to your toolbox of skills in Blender. If you found this tutorial helpful, definitely check out other simulation nodes tutorials on my channel, and of course all the other tutorials that are present. I release videos every single day, so if you like this content, be sure to subscribe. It really helps out a lot. Until the next video comes out tomorrow, thank you so much for watching. Keep creating and stay creative.